Hi everyone, and welcome back. So this time we're going to be talking about graphical solutions. It sounds crazy because it's awesome. Or maybe it doesn't sound awesome to you, but I think it's awesome, so let's learn about it. Okay, clicking over here, graphical solutions. Okay, now all of our making charts has been great, but what is it ever going to help me? I mean, yeah, it's cool for showing data, but how can I actually solve something using it? Well, we're going to learn about that today. For example, let's say you look at your light bulb. Turn the light bulb on, it's using energy. How much? Because light bulbs are rated in watts. They're rated in watts, so 50-watt light bulb is using power. It doesn't tell you how much energy it used. Now, if I wanted to, I could plot my light bulb's power use. Perhaps I turned it on, and I left it on, and I went down, turned it off. And I remembered I missed something, so I turned it on again, and then I turned it off. Well, if I understand how power and energy are connected, which I do, power is equal to energy over time, what I then realize is that energy is equal to power times time. And this should kind of remind you of like a rectangle, like an area of a rectangle. So if I look at my plot, this is power versus time. What I see is that the area of these two rectangles, that's how much energy I used. If I know what this area is, I can determine the energy. And so if you can work out the area, it's just base times height and base times height, add them together, you can get it. So try that here, type it in, see what you get. Actually, I'll do this one with you. So 50 times 2, that's 100. And then 50 times 3, that's 150. So 100 plus 150, 250. And good, we did it. Woo! So you solved that. You figured out how much energy you're using based on this plot. It made it a lot simpler. Okay, we can also do the reverse. We can look at our total energy use, like how much total energy we used, and figure out what's the power draw of some sort of item. And what's the power draw on average, or what was power draw total? So look at this, power is equal to energy over time, and energy over time, maybe that reminds you of a slope, like rise over run. Because if I look at this, you see there's a slope for these lines. And I'm just guessing here, just spitballing, and I already know that you're correct. Power would be the slope of this line. So if I look at how much the energy increased here over the time it took, what I'll find out is that if I divide those two, it'll come out to 50. So let's look from 4 to 7 seconds. So the change in time would be 3 seconds. Okay. The increase in energy goes from 100 to 250, so the change would be 150. Good. And if I divide those two, what I get is 50. Don't worry about the units too much right now. We'll learn about those later. But there you go. It worked. The slope of that line was our power draw. And just as a note, that little triangle right there, that's a delta. And it means change in. It's a capital delta. It's a capital D in the Greek alphabet. Yes, Greek is something you learn as an engineer. Not how to speak it, but just the letters. Okay, we'll do one more. We'll do one more, and then we'll stop here, and we'll do some more next time. So the last one is we can actually. Sorry, one note. Then I'll end with this one. Now notice that if you see things that are multiplied together in equations, you might be able to solve it by plotting it, and then taking an area. Or if you see things that are divided in an equation, you might be able to plot it and solve it by using the slope. But you might be able to. It's a possibility. Some things don't work that way. Things that are functions of time typically work. They typically work great. Other things, not always. So just keep that in mind, okay? Keep that in mind. Okay, with that, stop here. I'll see you all next time. Bye-bye.